Now that we have seen the chemical reactions, at least some of them, for organometallic chemistry, we can move on to catalysis and catalytic reactions. That is, and has always been, one of my main goals for this unit, is to get you to understand a little bit about catalysis. So we are in week 2, lesson 3. So let's talk about what my goals are for this part of the course. So if I have given you a mechanism, I want you to be able to name the elementary steps, and the way to name those steps is to do the electron counting. What's the valence number? What's the DN count? What's the coordination number? And figure out what's happening between molecule A and molecule B so that you can name the elementary step. If I have not given you the steps, then I might ask you to propose reasonable steps given the mechanistic steps that we've seen so far, the various reactions: oxidative addition, reductive elimination, insertion, elimination. The catalyst identity, so what is the structure, the DN count, the valence electron count, oxidation state, or valence number of that catalyst. And I'll usually give you the catalyst, but sometimes usually what you would dissolve into the solution is not the catalyst. The catalyst has to undergo some sort of activation process or lose a ligand to get to the active catalyst. And something to remember about catalysis is it's all equilibrium. If you find yourself going down a pathway that isn't productive, you can always Le Chatelier your way backwards to something and then try a different reaction step and see where you can get from there. I always encourage Chem 104 students to use Le Chatelier as a verb. I usually give bonus points for such usage. However, I cannot encourage use of Le Chatelier as a verb in other courses. Before we go any further, let's talk about what a catalytic cycle is. So we start with a reactant. We want to convert it into a product. And how do we do that? We use a catalyst. And the catalyst reacts with the reactant to form complex D. D turns into A turns into B. B may go off to form product. B then turns into C, which then undergoes some additional chemistry to form D. So this keeps cycling around and around, and the catalyst does regenerate itself. But remember, what you dissolve in solution maybe is over here, and it turns into the catalyst. The catalyst is usually off cycle. What you dissolve into the solution is off the cycle from the main catalysis. We're going to look at two different reactions, hydrogenation and hydroformylation. These are two sort of classic, old school catalytic cycles. They are some of the first that were studied well and that were carried out on large scale. I already mentioned this. If you need to, you can always use equilibrium to get yourself out of a place you don't want to be. And good catalysts are unstable. So we have talked about in my class how 18 electron compounds where you filled all 9 of the valence orbitals tend to be more stable. That's not what we want for a catalyst. If the molecule is stable, it's not going to be very reactive. Active catalysts often are at a lower electron count or a lower coordination number than what we might expect for a stable complex. And so we usually can't observe the catalysts that are doing the reaction. We have the pre-catalyst, what you dissolve in solution, that then turns into something else to do the chemical reaction. Okay, so what are the mechanistic steps that you are allowed to use? And maybe allowed is the wrong word, but I don't want you to ever propose a step that we haven't talked about in class. I'm not going to try to trick you. So oxidative addition and reductive elimination, that is a step that you should be able to propose. The 1,1 insertion, so the carbonyl insertion or migratory insertion. The 1,2 insertion, which is seen with olefin chemistry. The reverse of that reaction is elimination in the case of the 1,2 insertion, or deinsertion in the case of the carbonyl insertion. The beta hydrogen elimination is a special case of an elimination reaction. Those are the 4 reactions that we've talked about in this part of the course, but we've seen other reactions. We spent a whole week or more on ligand substitution reactions, so that's certainly allowed. You can take a ligand, take it off the metal, put a different ligand on the metal. You can also rearrange, so if you know for some reason that you need to have 2 ligands cis in order to do a cis reductive elimination, and the 2 ligands that you want to do the reductive elimination are not cis, rearrange. Not all complexes rearrange, but for the purposes of this class, it is safe for you to always propose a rearrangement reaction. We have not talked a lot about redox in this class, but certainly if there is a external oxidant or reductant, you could use that to do redox chemistry. For this year, 2020, I will almost certainly give you that information if you need it because we really haven't talked about it. Metathesis, salt elimination metathesis specifically, that was a reaction that we talked about specifically for either adding a lithium alkyl to a metal or a lithium amide or a sodium alkoxide to a metal chloride. So that's a reaction that can take place, so don't forget about that one. And then protonolysis is a reaction that is specific to amides and alkoxides where you take a metal alkyl and a phenol and you make the metal alkoxide and eliminate an alkane. One very important reaction that we will not talk about this year is the 2+2 cycloaddition. This is a reaction that is super important. Olefin metathesis won the Nobel Prize for Grubbs, Schrock, and Chauvin in 2005. So it's a very important chemical reaction, and it's not one that we're going to talk about in this class at all this year. Okay, let's look at hydrogenation with Wilkinson's catalyst. So Wilkinson's catalyst is this catalyst here, rhodium chloride tris triphenylphosphine. So Wilkinson, after he was done discovering the true structure of ferrocene, then went on and worked on a lot of different areas of organometallic chemistry, and this catalyst is named in his honor. He was working on the hydrogenation in 1965. This catalyst catalyzes the hydrogenation of many different types of substrates. The old school way of doing hydrogenation was palladium on carbon. Perhaps you learned that in organic chemistry. But this allowed a solution phase catalyst allowed for really careful mechanistic work so that we could really understand how the chemical reaction took place. And so some of the information that we learned because of these careful studies is syn addition. So both hydrogens end up on the same face of the olefin after the chemical reaction. It's not obvious in this simple chemical reaction, but if this was a prochiral olefin, what that means is once you've hydrogenated it, it becomes a chiral alkane, that those hydrogens end up on the same side of they both add to the same side of the CC double bond, and you can make a chiral alkane that way. The rate determining step of this reaction involves metal hydrogen bond breaking. It's a primary deuterium isotope effect. We're not going to talk about deuterium isotope effects in this class this year. It comes from the reduced mass calculations I've had you do for IR. Basically what that means is a metal deuterium bond is at a lower energy than a metal hydrogen bond, and so it has a slower reaction. It's got a higher energy well to climb out of. And that's just not something we're going to have time to talk about this year. So these are some of the facts about the reaction. Any mechanism that we come up with is going to have to account for these facts, and so let's see what we can do in terms of proposing a mechanism for hydrogenation with this rhodium compound. I'm actually going to play along with you at this point, and I'm not going to look at the next slide, which has the answer. I'm going to try to figure out what this mechanism is on my own. I actually know the answer, but I don't remember actually the exact order of steps. And so I'm going to propose some reasonable steps and sort of talk through them and see what we can do. So we know that we've got this rhodium compound. It is a D8 ML3X complex. It's 16 electron square planar, and we expect it to undergo a reaction. So the two possible reactions that it might do is oxidative addition of dihydrogen or addition of the olefin as a new ligand to go to a 5-coordinate complex. I'm going to pick oxidative addition of H2. And so let's see where that gives us. So we're going to add H2. That is a nonpolar substrate. That should give us a cis product. Okay, so if I had a better Apple Pencil, I might have less kindergarten-looking drawings. But there I've done an oxidative addition. Those two hydrogens are cis to one another. Now I would propose that one of the ligands is going to fall off, and I'm going to add the alkene. So I'm going to do a ligand substitution reaction. Okay, I've lost an L. Oh, I didn't draw it, so there's an L going away from our reaction. And we have L2X rhodium dihydride ethylene complex. Now I'm going to do a 1,2 insertion. I'm going to take this ethylene and do a 1,2 insertion into one of these two rhodium hydride bonds. Okay, the next step I want to do is, well, let's look. I've gotten closer to making product. I know that in the final product I want to have a CH and a CH, and I formed the first CH bond. Here's a carbon and a hydrogen. I know that I want to form that bond. A way that I can form that bond using steps that we've used in class is a reductive elimination. That's going to give us our desired product and regenerate our complex if we add another L ligand. So let's do that step and see what happens. All right, there's my reductive elimination. I have formed the product of the reaction, so this comes over to here. And what I need to do also is I need to add an L ligand back in. So the L ligand that started out over here that I lost originally is swimming around in the solution. Eventually it comes over here and adds back to the complex. So this is a perfectly reasonable catalytic cycle. One thing I have not done and that you should practice doing is to make sure that you can do the electron counting. So I did it for this complex. This was a D8 rhodium XL3. This is a rhodium D6 X3L3 18 electron complex. So go through and make sure that you can do the electron counts on these compounds to make sure that you can use those electron counts to verify the reactions. All right, on the next slide, we're going to go through additional data to show that this mechanism is wrong. However, it would be acceptable for Chem 104. These are all reasonable steps. They just turn out to not completely match the experimental data that Wilkinson observed. Okay, here is the real mechanism of Wilkinson hydrogenation, and I got a few things wrong. First of all, the first thing that happens is we remove one of the ligands, so this is a triphenylphosphine. It's replaced with a solvent to make this higher energy complex. We talked about this in the section when we were doing ligand substitution reactions. The solvate complex, that rhodium solvent bond is really bad. It makes this a higher energy species, and it gets us into the catalytic reaction manifold, which is a higher energy manifold. So once we form this complex, it can do an oxidative addition, so I was right there, except for the solvation. We then do the the ligand addition, so we replace the solvent with the ethylene. So this step, if it were what I drew, which is replacing a ligand with the ethylene, it just isn't favorable. Replacing the solvent with the ethylene is what actually happens. I didn't draw a solvent coming in when I did the 1,2 insertion, so that's one step that I missed. And one thing that sometimes happens is just based on the geometry, you might end up with your hydrogen and your carbon that you want to do the reductive elimination with. Instead of being cis, you might have accidentally had it be trans. And you can't do a reductive elimination of a nonpolar substrate from a trans orientation, so you would have to do some sort of a rearrangement to get the cis positioning. That's something I really value, and when you do your homework or your test, make sure that you show that you get to the cis position, because reductive elimination for nonpolar substrates has to be from cis, and that demonstrates that you understand it. We do that, we generate the product, regenerate our catalyst. And so notice our active catalyst is not what we dissolved in solution. It's this solvated rhodium L2 chloride. It's actually even more complicated than that. The complexes that are in red boxes are the only complexes that were observed, and they were using IR back in the early 60s. So complex 30 here was observed. Complex 31, 32, and 33 were all complexes that were observed, but they are not part of the catalytic cycle. They're off the cycle. And some chemistry takes place. So what I propose is hydrogenation, oxidative addition to form complex 30, but that just, the energy to get into the catalytic cycle from complex 30 is just too high. And so it actually goes back, loses solvent, and then does the oxidative addition. And so the proposed cycle here in this diamond is what's believed to be taking place, although none of those species were observed. And that's an important take-home message. If you can observe it, it's probably not catalytically active. This dimer is actually a shutdown on the catalyst. It sort of it can precipitate from solution, or it doesn't do anything. It's much harder to get in once you've done that. This dimer as well is sort of an end of the catalytic cycle. So what you propose for Chem 104 may not be actually what is true, but if your steps are reasonable, I will accept them. All right, let's move on to cobalt catalyzed hydroformylation. This is an extremely important reaction. It's the synthesis of terminal aldehydes. Of course, all aldehydes would be terminal. If it was internal, it would be a ketone. But N+1 aldehydes from N alkenes. So you can take an alkene and synthesis gas, which is a mixture of methane and water, which, well, synthesis gas is carbon monoxide and hydrogen, but you can actually make that from methane and water, and you can make it from the gasification of coal. Coal is super cheap, water is cheap, heat it up, you can make carbon monoxide and dihydrogen. So you can make a very valuable product that's useful for glues and all sorts of synthetic chemistry. Aldehydes are a really good functional group from an alkene, which is pretty easy to get to in a pretty straightforward way. So this is a very important reaction. It was done on a huge scale, and rhodium is a way more expensive than cobalt. It's a second row transition metal, so it's going to be a lot more expensive. And so if you're using rhodium to make a very simple hydrocarbon, you know that it's got to be very, very effective. So the rhodium catalyst is way better than the cobalt catalyst. The textbook chapter talks about that. It allows you to do it in lower pressure, lower temperature, and it gives better branch to linear ratios. But the important part is we want to make this chemical reaction take place. And you can sort of see what's happening. We are doing a carbonyl insertion reaction somehow. So this blue carbon ends up bonded to the red carbon from carbon monoxide. We've done a hydrogenation somehow. So we sort of know what bonds we need to form. Let's see if we can propose a cycle. The active catalyst for this reaction is dicobalt octacarbonyl. This is an 18 electron cobalt carbonyl. 18 electron compounds are not very likely to be very reactive, so it doesn't seem like that's going to be a good active catalyst, and it's not. The first step of the reaction is actually breaking apart this dicobalt octacarbonyl into a monomer, doing a oxidative addition that looks different from the ones we've seen before. So oxidative addition, if we take one dicobalt and one dihydrogen, we can form this new species, which the net change in oxidation state is +2. We've gone from cobalt 0 to 2 cobalt +1s. So this is the active catalyst species, a cobalt XL4 compound. I'll let you do the electron counting on your own. That's how we're going to start the catalytic cycle. The next slide goes into some detail about the catalytic cycle. What we're going to do is, instead of proposing a mechanism, I'm going to give you the mechanism, and you can try to name the steps, do some electron counting, and see where we can get. Okay, so here's our dicobalt octacarbonyl. We add dihydrogen to form this 18 electron cobalt hydride tetracarbonyl compound. Cobalt is in group 9, so 9 plus 1 is 10, plus 4 times 2 is 8, so that's an 18 electron compound. So the first thing we want to do is be able to identify, using CBC notation, our different species on here. So I've given you this cycle, so the first thing you should do is label all the compounds, then determine their electron counts, and then we will name the different catalytic steps. So before I go on to the next part of the video, pause it right here, determine the electron count, oxidation state, coordination number for compound, they're not labeled, but this compound, this compound, this compound, this compound. And that way you'll know you're doing it correctly. Okay, hopefully you got this to be a 16 electron compound. We started with 18, we lost an L ligand, so it better drop by 2, that's 16. Here, we've added an L, so we're going to go back up to 18. Here, we've just done a rearrangement. Well, more than a rearrangement. This is an 18 electron compound. It's cobalt LLLLX, so cobalt L4X is 18 electron compound. So hopefully you were able to do that. Now let's try to figure out what the names of these steps are. So this first step, we've lost a ligand. That's probably going to be a ligand loss or a ligand dissociation reaction. Here, we've added a ligand. So step 1 and 2 combined are a ligand substitution reaction. So sometimes you can just draw those 2 steps in one, but the reason why we've drawn this in a 2-step process is that this is not the active catalyst. This is the active catalyst. And so we need to have the lost ligand as our starting point and then add a ligand to get around our cycle. So we've added a ligand. Here we've done a 1,2 insertion. So we've added a hydrogen to this terminal carbon and then forming the bond to this carbon. One thing I should point out, this inner circle is the linear aldehyde. So this is actually the desired chemical reaction. The outer circle is the branched aldehyde, which is less desirable in terms of its properties. So we've done the 1,2 insertion to get there. Now we do a 1,1 insertion, migratory insertion, where we've taken and inserted the inserted the carbonyl into the cobalt carbon bond. This step, there's a lot going on. I'll show it on the next slide, and we get back to here. So there is a lot that happens between compound 4 and whatever this compound is. One thing I want to point out, the only thing that's observed in the IR is this, where we've now added a carbonyl to here to get to an 18-electron acyl type compound. That's what's observed in the IR. It's got a large equilibrium constant over to this side, but it's not catalytically active. It's got a Le Chatelier back to get going around the cycle. Let's look at the next slide and see what the actual names of the steps that I put in are. Okay, step 1 is dissociation. Step 2 is association, so it's a dissociative ligand exchange process. Then we have a hydrogen migration known as a 1,2 insertion, and we've added a CO. I didn't notice that on the previous slide. We had 3 COs, we've added one more to 4, so there's 2 steps in one here. I encourage you to write out each step individually, but sometimes they're drawn 2 at a time like this. Then this is the 1,1 insertion, and then the magic that takes place in step 5 is on the next slide. So we have cobalt XL3, a 16-electron compound. What happens is we add dihydrogen in an oxidative addition to go to the cobalt X3L3 18-electron compound. Then we do a reductive elimination, giving us our aldehyde product and regenerating the cobalt L3X starting catalyst. So that is the step 5 that is a little bit complicated on the previous slide. That's because there's 2 reactions drawn in one. So that's the end of this lesson in terms of old school catalytic cycles. Lesson 4 will cover the Suzuki coupling and CH bond activation. So some more modern catalytic reactions that have found wide use in terms of the Suzuki reaction, wide use in chemical synthesis, and CH bond activation is kind of like a holy grail for the field of organometallics. Can we figure out how to selectively activate a CH bond?